In this lecture, we're going to revisit the topic of quantum numbers, which again is a little abstract, using a simple little analogy that students generally find helpful. Okay, so we got an abstract topic. Let's go ahead and map this onto a nice simple picture. Okay, and we're going to talk about orbitals essentially as electron homes. Remember, orbitals are the description that describes how electrons exist around a nucleus. Right? Well, that's basically where the electron lives. So we're going to call that the electron home. Okay, so we've got a bunch of these different orbitals. So if we take a bunch of these orbitals, right, we put them all together, we can build up houses. Okay, and so each individual orbital with a specific label, which we talked about in the previous section, we can identify these orbitals with specific labels N, L, M sub L, corresponding to what we call these quantum numbers. Each one of these sets of quantum numbers are going to correspond to a room, and that's going to be the room where our electron lives around that nucleus. Okay, so all of these rooms and the houses that are built up of all these rooms are situated around individual nuclei. All right, so once we have that sort of analogy built up, then these quantum numbers that we've been talking about essentially provide addresses or locations for each one of these electron rooms. And the constraints, the relationships between the possible values that these quantum numbers can take are going to correspond to rules that govern the construction of electron homes. Hey, so I really want you to think about this very simply. The key with understanding this concept is actually to just accept things as they are and don't go too deep into it. The first half of this lecture content, we were talking about all the strange quantum mechanical behavior that's going on. Really wanted you to focus in and try and make sense of all of it. Now I'm going to actually ask you to do the opposite and just accept some of these basic rules and see where they take us, and then we'll come back later on and try and bring some more meaning in. Okay, so I'll very rarely ever say this, but do not overthink these concepts for right now. Okay, so we are going to boil this down to a very simple picture where we're going to think of these orbitals as rooms for electrons. So let's draw a little orbital as a little box, a little room where we can put that electron centered around that nucleus. Okay, and now we're going to denote an electron using a little arrow. Okay, and for reasons that we'll discuss a little bit later, these arrows are going to be pointing in a specific direction. So for right now, we'll just take a little electron designated by this arrow pointing down. And then we're going to go ahead and put that electron in a room, in its little orbital room right here. Okay, so this is going to bring us to our first rule of housing. Quantum housing rule for electron. Rule number 1 says that you can never have more than 2 electrons in a room, or you can never have more than 2 electrons in an orbital. Furthermore, notice how I oriented the 2 electrons that are residing in this room here, this orbital. One of these arrows is pointing up, the other one is pointing down. And so that's going to give rise to our next quantum housing rule, which says that electrons occupying the same room must face different directions. Okay, and again, we'll come back to that later on. For right now, just sort of accept it at face value. In order to place 2 electrons in a given room, they have to be facing opposite directions. And then we're met with a problem, right? Once we have 2 electrons in the room, they're facing opposite directions, but that room is filled. Okay, so that's our quantum housing rule. We cannot fit another electron in this orbital. Okay, this orbital is what we call full. Okay, the room is full. No more rooms for rent. So if we have another electron that comes along and he wants a home, then we're going to have to do something else here, right? Well, if that electron can't go in this room, but we want to associate another electron with the nucleus, what are we going to do? Well, we're going to have to start building up an electron home. It can no longer just be that single room. We're going to have to add on more rooms so that we can accommodate more electrons. Okay, so here's our next quantum housing rule. Okay, so the quantum housing rule number 3 tells us that if we are going to start constructing an electron home, these electron homes always have to be square. So you can't do something like this, just put 2 rooms side by side. You can't do something like this, put one in the middle up here. None of these things will work. They must remain square. Which means that if we add on another set of rooms, we're going to be adding 3 more rooms. And if we need to add on even more rooms on top of that, we are going to end up having to add 1, 2, 3, 4, 5 different rooms. Again, because we have to maintain that square, the same number of rooms, going off the vertical and horizontal directions. Similarly, if we have even more rooms beyond 5, then we're going to end up having to add an additional 7 rooms. Okay, so to map this onto what we talked about before, each one of these stories that we add to our electron home corresponds to the different subshells that we introduced in the previous lecture. So the first room that we add, that corresponds to the s orbital subshell, right? The p subshell is then denoted here in yellow, the d in green, and the f in blue. And so as we add up each one of these additional stories of the home, we can then monitor how many different electron rooms we're creating. Well, if we just have the 1-story room, we just have a single orbital right here. But when we go to that 2-story home, we have that original orbital plus 3 more, so then we're left with 4 orbitals, okay? And if you add on an additional 5 more, then you're met with 9, and so on and so forth. Add that additional 7, and then you have 16.